carbonate, but when calcium hypochlorite reacts, the product is calcium carbonate. Actually, when calcium hypochlorite reacts with carbon dioxide, the first step is also the formation of calcium bicarbonate. This step follows the principle of a stronger acid producing a weaker acid. We know that carbon dioxide and water form carbonic acid, and carbonic acid is stronger than hypochlorous acid. Therefore, carbonic acid can be used to produce hypochlorous acid. But after one hydrogen from the carbonic acid is taken by the hypochlorite ion, there's still one hydrogen left, which forms the bicarbonate ion. Since the acidity of the bicarbonate ion is less than that of hypochlorous acid, the hydrogen in the bicarbonate ion cannot be taken by the hypochlorite ion anymore. This is why when you bubble carbon dioxide through a sodium hypochlorite solution, the final product is sodium bicarbonate. But if you replace sodium with calcium, it's a different story. We know that the bicarbonate ion undergoes ionization in solution. Normally, the carbonate ions produced by this ionization are not enough to form a precipitate with calcium ions. However, due to the presence of hypochlorite ions, they can take away some of these hydrogen ions, causing the ionization equilibrium of the bicarbonate ion to shift to the right. The concentration of carbonate ions in the solution increases, and they can then form a calcium carbonate precipitate with the calcium ions. So, in reality, another reaction step occurs. Adding these two reaction steps together gives you the overall reaction equation. It's important to note that in the reaction where calcium hypochlorite and carbon dioxide produce calcium carbonate, the carbon dioxide is the limiting reactant. If there's an excess of carbon dioxide, the product won't be calcium carbonate, but calcium bicarbonate. So this equation is for when carbon dioxide is the limiting reactant. If it's in excess, the subsequent reaction to form the precipitate won't happen, because if carbon dioxide is in excess, there will be a lot of carbonic acid in the solution. In this case, the hypochlorite ion will take a hydrogen ion from carbonic acid, not from the bicarbonate ion. This is because the acidity of carbonic acid is stronger than that of the bicarbonate ion, so carbonic acid gives up a hydrogen ion more easily. The second case is through redox reactions, where a weak acid can produce a strong acid. The three reactions below are common on tests. The first reaction is often used to prove that the non-metallic character of chlorine is greater than that of sulfur. In the second and third equations, sulfur has an oxidation state of +4 and has strong reducing properties. Sulfur with an oxidation state of -2 in the first reaction has even stronger reducing properties. All are easily oxidized by certain oxidizing agents. Chlorine gas here can be replaced with other halogens like elemental bromine or iodine, and the reaction still occurs. Sodium hypochlorite below can also be replaced with a halogen. This is how, through redox reactions, these weak acids can be used to prepare these strong acids. The third case is the formation of a volatile acid. Acids like hydrochloric acid and nitric acid are volatile, while phosphoric acid and sulfuric acid are non-volatile. So in the lab or in exam problems, if you need a small amount of hydrochloric acid or nitric acid, you can prepare it using a non-volatile acid. Of course, besides concentrated phosphoric acid, you can also use concentrated sulfuric acid.